Welcome back to part 2 of chapter 16 on stochastic volatility. So we're now going to introduce the model that we're going to try fitting to this S&P 500 data. And so I'm going to introduce this idea of volatility leverage. And this is based on the fairly well-established empirical result that when the stock market has a big drop that's associated with an increase in volatility, it's called leverage. It's somehow an asymmetry. Drops and positive jumps in the market don't have the same volatility consequence. This is something that the Garch and Arch model can't explain. And so we're going to formally define leverage Rn as the correlation between index return on day n-1 and increase in the log volatility from day n-1 to day n. And so that could be positive and it could be negative. And so I guess our claim is that it is correlation between index and increase. So if the index goes down, the volatility goes up. So we're thinking that Rn is maybe going to be negative, but we'll have to see what the data say about that. So models have been proposed which incorporate leverage into the dynamics via a kind of stochastic volatility framework, and we're going to use the model developed by Bretto 2014, and in this context, the leverage Rn is modeled as a random walk on this transformed scale. And so it's a sort of x-bit transform, and Gn is a Gaussian random walk. So let's have a look at, we'll see the equations in a little bit. So in a special case of this model, the Gaussian random walk has 0 standard deviation and you get a fixed leverage model. In general, the leverage may change through time. And this is something that you can put into many POMP models. Whenever you have a fixed parameter in your dynamic model, you can say, well, is it fixed or is it actually slowly varying with time? And by putting a kind of random walk term into it, you can allow it to vary with time. And this will generally give you a non-Gaussian POMP, because even if your original model is Gaussian, and even if the perturbations are Gaussian, then generally the parameters don't necessarily enter additively with the latent process. So for instance, the parameter might be multiplicative with the latent process. And then so even if those two things are Gaussian, their product is not Gaussian. And so you get a kind of non-Gaussian system, but that's not a problem when you're doing these simulation-based methods for POMP models. You can still fit that system. And so this is just generally something that has use outside these stochastic volatility models, but here's an example of that idea. Okay, and now we come to the equations. Here we see in equation 4, Hn is the log volatility, and so it has an kind of an autoregressive term, and then it has a leverage term where the Rn that we see in equation 5, and then the this Gn that defines Rn is doing a random walk here. And so beta n is the is basically related to the return yn, and the epsilon n's and nu n's and omega n's are IID normal sequences. So So that's a model. It looks a little bit complicated, but you can imagine it's not that hard to write a simulator for this model. So we can write an R process in principle, and then we could get going. But there is a little wrinkle in this model, which is that kind of the natural choice for the state vector is Hn and everything that's needed for the dynamics of Hn. But when you look at the equation for Hn depends on this beta, which depends on the previous returns. And the Yn's are the observations. So the observation is getting caught up in the dynamics. And we gotta do some thinking about that. Okay. As I just mentioned, there's this problem that the Yn enters the dynamics. That's a violation of the POMP structure, because the POMP structure says that the latent process X is going ahead doing its latent dynamics, and then it throws off measurements Yn at each time. This kind of violation isn't so uncommon. For example, it happens a lot when you start modeling control. So if you have a controlled system, then that means that there's something is done to the latent process, and how is it controlled? Well, it has to be controlled based on what you measure. So the control is going to be some function of Yn, and so the control dynamics are going to have the observations entering. Now, we can extend the POMP model to deal with this situation, and so, well, that's what we have to do. Okay, so here's a way to extend the POMP model, which in some ways trades one problem for a different problem. Let's put Yn into the state process. So now Xn is Gn, Hn, Yn, and the measurement process measures the Yn component perfectly and doesn't measure Gn and Hn. Formally, this is now a POMP model, but it's a POMP model with zero measurement error on the Yn component that we've decided to put into the latent state, and we can do that formally. There's no reason we can't. But this breaks the particle filter, and to see that, you have to see why the particle filter needs measurement noise to work. If you don't have any measurement noise and you have a normal continuous model, then none of the prediction particles that you propose in the particle filter are going to land in exactly the right place to have infinite weight. They're all going to have zero weight instead. So we're going to need to modify sequential Monte Carlo, and we're going to have to hold tight and see how to do that. Well, to do that, let's write the filtered particle as the G component, which is to do with the leverage part, and the H, which is the log volatility, and the measurement, because we put the measurement into the latent state process. Now, we can draw G and H from the latent process, kind of ignoring the Y's, and then we can weight it according to the likelihood of Yn given Gn and Hn, and with a bit of care, we can still get a properly weighted particle filter out the other end. And some of the algebra for this is given in the appendix. I think I'm not going to say more about that now. what we want to do is we want to see how this structure can be implemented in POMP. Well, when we do the prediction particles, the observation still appears in the in this transition rule for G and H. And so somehow, if we want to code that up into POMP, the R process has to have access to the observations. And so let's think about how we can do that in the POMP package. Well, how can we give our process the observations? In the standard POMP, it doesn't have that, but a standard POMP does have the covariates. And so if we put the data in the covariate slot, then we can access that within our process, and we're in a good situation. But that's all very well when you're simulating conditional on the data. When you're trying to simulate new data, then you can't do that because you don't have the data to put in the covariate slot. You're busy generating the data. So it turns out that we end up needing two versions of the POMP object. We need one version that's in the right form to do the filtering, where the yn is the data, and then we need another version for simulating new data sets, say for testing out the methods where new data are generated. And so that's what we're going to do. We're going to write two versions of the POMP object. And well, the mechanics of writing out the POMP object are relatively well known to us by now. So what I'm going to do here, I'm going to start by just listing the state names, the param names, the regular parameters, and the initial value parameters. And here they are. Now I can write the C snippets, and I have an rproc1 and then I have two different versions of rproc2, one for simulating and one for filtering. And for simulating, I generate a new Y state. For filtering, I use the actual data for my Y state. And then once I've written the code in these two ways, I can get two versions of the R process by pasting together the common part with the specific part for these two cases. So rproc1 is intended to faithfully represent the equation that I wrote down above. So you can check whether it does that successfully. Maybe that's all I can say about that right now. We need initializers, and we need an R measure, and we need a D measure. This is all just a matter of being faithful to the equations. We need parameter transformations. So sigma eta and sigma nu are non-negative. Well, they're positive. We're going to log transform them. Phi takes a 0,1 value, so we're going to logit transform it. And we can then build a POMP object suitable for filtering and parameter estimation, and then we can do iterative filtering. We could do a method called particle MCMC, which is a kind of putting a particle filter likelihood into an MCMC algorithm, and that's one of the other methods that we mentioned in I think it was chapter 14. And the data are placed in a covariate slot, as we mentioned, and that kind of tricks the POMP package into doing what we want with our model. And so I think this is basically what I was explaining before about how we use the covariate slot to insert the data where we need it in our process. And so now we just have to go through the mechanics of putting the data into the covariate slot. And so here we go. We've seen a covariate before in the polio analysis. So this is basically the same kind of trick. We have to make a covariate table and put it into the covar slot of the call to POMP. And that is what's going on in these lines here are the building the covariate table. I think everything else going on here has become quite familiar through all the POMP examples. We're just passing the components of the POMP object that we've built into the POMP object. Now, when you want to develop an analysis, in some sense, for the likelihood, you don't need to simulate from the model, right? You only need to filter from it, but it's really good to check that you can simulate too, because that provides a good way to test your code. You can then check that your filter out on your simulated data when you know the model, whereas when you take your filter to the data, if things go weird, you don't quite know whether it's your model being wrong or something that you coded being wrong. Well, when you're doing it on simulated data, you know the problem isn't model misspecification. So to simulate, we need to choose some parameters. Here are some parameters, and then I'm going to simulate from the POMP model with these parameters, and when I want to filter this simulated model, I have to swap back the data that I simulated into a filter POMP, and here's the code to do that. So I stick in as covariates the data that I'd simulated in sim1.sim, and then I also need to make sure that my R process is the filter version of the R process, and then I have a POMP suitable for filtering using the simulated data built with the POMP suitable for simulating. Okay, so now we've got something that we can say check that we can filter, and filtering on simulated data is often a good step before we go to filtering on the actual data. And we could also check parameter estimation on this, by re-estimating parameters by iterative filtering, for example. And we have to figure out how much computer effort to use. As we saw in the polio case study, it's often really convenient to have 3 different run levels: a kind of debugging run level where everything runs super quickly, a medium run level, and then a kind of production level run level that you only do when you're fairly sure that your results are in pretty good shape. You just need to wait longer to get a cleaner set. And so we're going to, I haven't defined all these variables yet, but you can maybe see where we're going. We're going to do a, we're going to do likelihood evaluation. We're going to do a local search. We're going to do a global search. And so we need to set up the sizes for all those things. And one thing I should say a little bit about, maybe when we get to run level 3, we may want to put the results, put the computations on a Linux cluster if we have one close at hand. It's quite helpful for this to have code that runs either on a Linux cluster or on your laptop, so that you can debug on your laptop and then the same code will run on the Linux cluster without extra rounds of editing between the two. And so here is some code to do that. Really, the only difference, right, is in the parallelization. And if you're only using a single node on a cluster, all you have to do is figure out how to tell R what cause it has. And so here's a little bit of code to do that. If you are on a Slurm cluster, then there'll be a variable Slurm ntasks per node that will tell you how many jobs you can run. And if that environment variable doesn't exist, then that'll give you an NA, and you can just do detect cause on your, and then presumably you'll be on your laptop at that point. And then you can just proceed with the parallel code, just exactly the same for a laptop. Then for reproducible computing, we're going to use this stew function, and we are going to save the file under different names depending on the run level. That's just for kind of organization. And here we're just going to do a likelihood evaluation by repeated p-filtering. Well, we hardly needed a cluster for that because that's not a super big job. We relatively quickly find the log likelihood with a relatively small standard error, only about 0.1 log units. And it turns out that only took 4.3 seconds, although maybe one of the reasons that took 4.3 seconds is because it was being run on a cluster. It would take a bit longer on a laptop. And we have to average the replicates using log mean x. You've seen that before. We do that since the likelihood estimate is unbiased on the natural scale, not the log scale. So we take the log likelihood, we map it back to the natural scale, do the averaging there, and then log it again. Right now, I don't think we're going to more extensively do a simulation test. We could do that, and we could, like by simulation, we could see how well the maximum likelihood estimator works on the simulated data. But here we're just going to get straight down to business and start fitting the model to data, and that'll be the next part.